Testing Lorentz symmetry. In relativistic physics, Lorentz invariance or Lorentz symmetry, named after the famous physicist Hendrik Lorentz, stated that the laws of physics are the same no matter which direction you are facing or how fast you are moving. In fact, this is a symmetry of spacetime. Over the past several decades, it was Einstein who used Lorentz symmetry to describe the law of physics in our universe. He took Lorentz symmetry as a postulate of special relativity, including the speed of light in a vacuum are the same for all inertial observers. That's why it is connected to the concept of special relativity. According to special relativity, there is no absolute space or absolute time. So if two objects are moving relative to each other in empty space, it would actually be possible for an observer to tell their absolute velocities. Maybe only one of the objects are moving and the other was stationary. But you wouldn't know which is which because their movements are relative to each other, not to any internal reference frame. One important consequence of Lorentz symmetry is that the speed of light is invariant or a constant in vacuum. The fact that the photon in vacuum always moves at a speed of just 300,000 km per second, in which Einstein related to his theory. But physicists test Lorentz symmetry at ever higher degree of precision, as violation of foundation property predicted by a number of proposals that aim to unify the two major theories of modern physics, general relativity and the standard model of particle physics. There is an experiment called Michelson-Morley experiment used interferometer in late 80s to measure the speed of light, which they hope would enable them to prove the existence of ether. They tried but they never saw any evidence. Interferometer is based on reflecting light back and forth between mirrors and consists of both optical and electrical components in interferometer. The cavities are carefully aligned at the right angle to each other to detect any tiny changes in speed of light along different axes. In the case of cavities, a change in speed of light would induce change in resonance frequency, but after analysis of full year data, no such changes was found. In 1980s, Planck's scale, known for its universal minimum limit beyond, in which the law of physics breaks, Max Planck proposed a set of units to simplify the expression of physics law. The Planck scale referred to either a very large energy scale of 1.522 times 10 to the power of 19 giga-electron-volt or a very tiny size scale of 1.616 times 10 to the negative 35 meters when the quantum effect of gravity becomes important in describing particle interactions. The Planck scale was invented as a set of universal units, so it was shocked when those limits turned out to be the limits where no law of physics applied. Lorentz symmetry of photons being broken on this regime, yet it didn't see any evidence for this. By providing the strongest evidence that the speed of light is constant, the results further verified that Lorentz symmetry is a basic property of nature, like other experimental results. The speed of light doesn't seem to depend on orientation of laboratory. The Lorentz symmetry of photon, it allowed the scientists to improve the bands of the speed of light. It improves a very useful experimental in testing theories that unify general relativity and standard model while physicists predicting Lorentz symmetry violation. Some of those theories are string-based model and a quantum gravity theory. By a near future, and by the help of modern physicists, they can develop or improve these theories, but now, it depends on how they thought and we knew.